Right. So my task is to talk about fish passage and monitoring. And my planned outline for that is this. So I'll introduce you to barriers in migrating fish, but I put it in italics because of all the great presentations yesterday. So that will be rather brief, I would say. And then I'll move over to talk a little bit about fish passage solutions, because that's what most of you are working on, but we didn't hear a lot about them yesterday. So I'll talk a little bit about that, and then move over to the main attraction, so to say, monitoring and evaluation tools. And I made a rough overview and division into the typically most used tools there. I'll go through them, talk a little bit about the specifics, and then I'll provide some examples. And then I will end by giving you two multi-tool case studies that we have carried out. And then I'll have a very short and powerful take-home message. At least that's the plan. Right, so barriers in fish. Freshwater fish are in trouble. That's the short version now after yesterday. I think we all agree on that. And of course, the freshwater mussels, Martin. Why is that? Well, obviously, climate change, overfishing, and also the presence of dams. And I think this slide, or some version of it, has been mandatory in most talks. So I think we can all agree on that. Europe is heavily fragmented. But the thing is that obviously not all these barriers have anything to do or something to do with hydropower. So most of the other barriers are obsolete, and we can remove them if we have the funding and if we have a good plan for in what order to remove them. But the dams connected to hydropower is a different story. But why do they matter? Well, we saw the theater play yesterday that really dug into the details here. I'm also, like Jörg, I like the cartoons of Seppo, so here's one of them. So even though the eel and salmon can't really agree on the details, they are both right. I mean, they are both diadromous species, so they rely on intact connectivity between freshwater and saltwater. And I just had to include these wonderful pictures by Jennifer Clausen, so showing the two life cycles. So with salmon being anadromous, they spawn in freshwater, stay a couple of years in the river before they move downstream to the ocean for increased growth. And then they head back after a couple of years to the natural stream. We all know this. And then on the other hand, the other extreme, if you like, is the European eel. That is catadromous, so it does the opposite. It spawns at sea, drifts towards Europe. Some, not all, eels enter freshwater for increased growth, and they stay 5 to 30 or even more years in freshwater before they need to go back to sea and cross the Atlantic Ocean again. So I mean, it pretty much boils down to same but different for these two species. So salmon moving upstream as spawners tend to aggregate below the first barrier at the turbine outlet. If they manage to get past somehow, after spawning, they return downstream as kelts, and a couple of years later, their offspring. And they, again, tend to aggregate at the turbines, but the turbine intake this time. So again, same but different for eels. The major difference here is that they move upstream as juveniles, worm-sized little creatures with a phenomenal climbing capacity. I mean, they can climb vertical walls unless they hit the dry spot, and then they fall down and have to start all over again, unless they're already eaten by some predator on the way. And the adult eels, again, 5 to 30 years later, also aggregate at turbine intake, but since they are masters of passing pretty much anything, they tend to move into the turbines and typically get chopped up into 1, 2, 3, or in 4 pieces. So again, this is the passage problem in a nutshell. We have to connect downstream with upstream for multiple species. Right, but then we do have some use of hydropower. So again, we can't just start removing all the hydropower dams when the electricity production on a global scale looks like this. We need more renewable power. We don't need less. So this is what we saw yesterday in the play with, on the one hand and the other hand, even though I won't be as dramatic when I go through this. But fact is that hydropower is the main reason, or considered to be the main reason, behind the declines of more than half of the threatened fish species in Europe. And of course, it's not just about fragmentation. We also have turbine passage, fish moving through turbines, getting injured or even killed. We play around a lot with rivers, so we divert water from one river to another, leaving the one river dry, or the opposite when we build dams and create reservoirs, in this case 170 kilometers long at Itaipu, and hydropeaking with aquatic organisms being faced with these conditions, ranging from more or less dry to flood conditions within a matter of hours, even minutes. So I would say that we still need our fish passage solutions. And I thought I would just start by showing you the definition of what we call FPS. So it's any device, structure, or mechanism which is designed or operated to facilitate safe movement of fish, of course, in an upstream and or downstream direction, plus one or several impediments. And this is the definition taken from the European standard for assessing FPSs. So we have kind of agreed on this, at least on a European level. And I think it was Rachel that used the same figure yesterday. So we can divide fishways for upstream passage into technical and nature-like fishways. The technical are typically made out of concrete and wood, and the nature-like are designed to mimic natural conditions. So we're building an artificial creek. And of course, the main idea, the goal with them, they have the same goal, and that's to help fish pass barriers that they cannot overcome. And two examples can be seen here. So obviously the nature-like fishways look prettier, and they require more space, but you can also include habitat in your design, so they can serve more purposes than just simply providing passage. Downstream passage solutions started to be developed a couple of 100 years later, I guess. And I expect some of you to disagree with me, but I'm simplifying things here. So I would say that this is the main solution at the moment: screens and racks. And we have the two main types, the inclined screen. So that's your powerhouse with the turbines. So the inclined screens guide fish to the surface where you have entrances bypassing the powerhouse. And the angled screens use the same principles, but instead they guide fish sideways to an entrance and bypass the facility. And again, two examples. So the inclined rack, this is a relatively, or a very large entrance to bypass. You can see it covers almost the entire width. And the angled screen with entrance over here. And then, of course, Velisara, we have bubbles and other interesting potential solutions, but I won't talk about them here. But I will mention this quick and dirty option for downstream passage. It's quite tempting. I mean, all power plants have spill gates. They are there so that you could release water that you cannot store in your reservoir or discharge to the turbines. And again, of course, it's tempting to just open them a bit and say, look what we did for the fish. But in most cases, they don't work. But I will show you one example, one case study in a bit. So what are we looking for here? What signifies the ultimate fish passage solution? Well, obviously, it, or they rather, should provide two-way passage, because typically you cannot solve both upstream and downstream passage with one solution. Apart from that, they need to be efficient, injury-free, and timely, so limited passage time. Shouldn't take too long for the fish to pass, and they should pass all naturally occurring species and life stages. I focus on salmon and eels, but that is because they suffered the most from fragmentation, and they're also more easy to study. But do such fully functional fish passage solution facilities exist? I would say, yeah. This is my favorite example that most of you, I guess, by now have seen before. So this works. It's very close to 100% both upstream and downstream. And I'll provide some details later on. But like Jörg was saying, obviously from the fish's perspective, the ideal solution is just to get rid of all the dams, all the barriers. But again, we need hydropower, at least for now, so that's not really an option when it comes to hydropower dams. So I talk about fish passage today, for obvious reasons, upstream and downstream, but just to remind you, of course, well, dam removal could replace all these solutions, but apart from providing passage, of course, we have to make sure that there is sufficient high-quality habitat upstream of the barrier in question, and that we have enough flow released so that fish can migrate and that the habitat is good enough. And then we have the unconventional tools. I'll provide an example later. And last but not least, we should never forget to include evaluation or monitoring in our projects, because if we don't know what we're doing, right? We can't really learn from our successes and failures. So evidence-based tools is what we need. Sounds obvious, but it's not. We're not evaluating all our remedial measures in RIBES. Right, so over to monitoring and evaluation tools. Monitoring is much more than tracking fish, obviously. So it's a tool to assess environmental conditions and trends over time so that we can spot if something is about to go wrong, or perhaps it already did, but at least we know what the problem is and can try to solve it. The program areas within the EU range from mountains, air, toxic substances to freshwater. And the freshwater monitoring programs are very extensive, and there are national monitoring programs covering lots of different parameters in our rivers. So this is just one example from a Swedish system with a network of study sites or monitoring sites. So for fish, in Sweden we have, I'm not sure what it's like in other European countries, but in Sweden anyone can access fish monitoring data online, which is pretty neat. And I'll provide an example of how we use this in research in a couple of minutes. So net fishing and electrofishing can be accessed by anyone online. So that's the way it should be, I think. But then we also have the EU data collection framework, the DCF, that monitor index rivers with wild populations of typically salmon and eel. And when I was preparing this presentation, I realized that Sweden is quite an exception when it comes to the DCF index rivers, because most countries had a bit of a slow start, didn't really find the best candidate. And so this network of index rivers is not complete yet, but hopefully it will be soon so that we can gather more information and learn more about what's going on. So what do applied research projects such as RIBES have to contribute with? Well, we can evaluate efficiency for specific measures and for particular species or even life stages. We can test new designs and innovative solutions, new methods, In some cases, we should stick to standardized methods, but we don't have to, right? We can think a bit outside of the box. And of course, we should have a more scientific and experimental approach. So I like toolboxes. And here's another one. So this is the very much simplified evaluation toolbox. So there's a range of different methods that we can use that is also used in monitoring, but I decided to divide them into capture methods, simply different ways of catching fish. If we don't want to touch the fish, fiddle with them, we can go for counters and just observe fish from a distance. And if we want to take the next step, we can tag fish so that we can ID them on an individual basis. So we can go for mechanical or electronic tags. And of course, we should also pay attention to the abiotic factors. Right, so I have a couple of examples. First, just very quickly, capture methods. We can talk about them for hours, obviously, but I will just mention that they are divided into passive and active. So with a passive capture method, you typically put out your capture gear, you sit and wait for the fish to enter. And with active capture methods, it's up to you to bring your fishing gear and go out there and find and catch the fish. And there's a huge range in the impact they have on the fish. So from limited or low impact to high impact, even lethal, if you use nets, for example, gill nets, that is. So my example is electrofishing that can be carried out by foot, like Daniele and Michele here up in Valle d'Aosta, or you can use the electrofishing boat to be able to fish deep waters, lakes, and so on. And they use the same technique, so you electrocute fish. So first you attract them, and if they get close enough, you stun them and you can collect them. We had this project on eel passage where we wanted to figure out what was different in regards of fish passage solutions between different sites on the Swedish west coast, where there were eels versus where there weren't any eels. So then we used data from the electrofishing database that I was talking about, and we compared the different sites. And what we found here was that the only fish passage solution that didn't have a negative impact on eel occurrence upstream of Cern Dam, that was nature-like fishways. For eel ramps and technical fishways, well, they were no better than dams without any fish passage solution. So from my perspective, after conducting years and years of manual fieldwork, this was pretty neat. Download data and get these results, which was pretty cool. So again, capture methods, you do fiddle with the fish. You don't always know how you impact their behavior and passage performance. So that's where counters could be an option. Video cameras or acoustic cameras. So video cameras have a low range, but you get really pretty pictures. You get high resolution images or videos of your fish and other creatures that pass through a fish pass or a fish counter. And then you have the acoustic cameras that use sonar technology and typically have a higher range, so you can cover at least the entire width of a relatively large river, but instead you get low resolution images. It makes it hard to tell the difference between species and sometimes even between a fish and a piece of wood. So all methods obviously have their pros and cons. So let's see if the music is turned off. It is, cool. So this is the huge nature-like fishway that I showed you from above earlier. And here is a video counter. And this is the first salmon that passed through this new fishway some years ago. So in this case, this was the optimal tool, I would say, to show us what happened after the fishway was improved. So, because we knew that there was a negative trend in regards of the number of salmon and trout spawners migrating upstream in this river passing this site. And after the fish passage solution was modified, we saw an increase. which was obviously good news. And the video counters, they are really improving quickly now. So this is just one example of the TIBA counter that most of you guys got to, learned a lot about, I guess, in Karlstad when you were there. But to me, it's pretty mind-blowing. I mean, you get the fish recognition algorithm, so it counts and IDs the fish for you. Works well even in turbid water. And you can even get information about if your fish lack an adipose fin or not, so if they're wild or of farmed origin. And it's easily accessed online as well. So that was a bit of a commercial break, I guess. But right, so there are all these tools, and it is pretty fantastic. So we went from the old fish way to the new fish way, but also from the old counter to the new counter. And with the new counter, all of a sudden, we realized that we had invasive species in the river that no one really saw before. And I think you can guess from the colors here what species I'm talking about. Come on. It's not that early. Thank you, sir. What else? The pink salmon. Right, so we have them in our rivers now. So we're probably making it slightly easier for them to proceed upstream with a new fish way, but what do you do? Right, so again, we get pretty pictures. We can use counters for a lot of projects, but we can't tell the difference yet between individuals. For that, we need tags. So mechanical tags, well, it could be pretty much any piece of plastic with a number on it that you attach to your fish. So when you recapture them, you can say, right, this is roach number 7. That was 500 grams when we tagged it. And I was struggling a bit to find a good example here, but this is what I ended up with. This is a very cool project. This is River Rönnoa, again down south in Sweden. So this is the catchment area of the river. There are only 3 hydropower plants on the main stem. They don't produce that much electricity. Could just replace them with a windmill, large windmill. And they're all being removed, hopefully next year. So we'll open up the entire system from sea to source. And our task here is to study how this affects the salmon population. And one thing we wanted to look at is the smolt production before and after dam removal. So we have used this screw trap with a guide arm to catch smolts. And all the smolts that we catch, we tag with a so-called streamer tag. So the piece of plastic with a number on it. We bring the fish back upstream, we release them to see, to study the recapture rate. And based on that, we can make a rough estimate of the total production total smolt production. So we had a recapture rate of 46% for salmon and trout, and it resulted in an estimated production of between 1,000 and 2,000 smolts, which is way lower than the previous estimates of more than 10,000 smolts of each species. So we did this year. We haven't really figured out yet what the mismatch, what's causing the mismatch. But we have the information now so that we can move on. So when we have our mechanically tagged fish passing the trap, if they don't end up in the trap, we don't have a clue what's going on, obviously. We don't know if they died or were eaten, whatever. So in order for you to track fish, you need to use electronic tags. And we heard a lot about different studies using electronic tags yesterday. So I thought I would mostly just comment on the differences between the methods that didn't really come through yesterday. So again, a range of different techniques. We have the satellite tags, radio, acoustic, and the pit tags. Right, so again, I think it was Rachel that had a fish. My fish is uglier and older for some weird reason. And right, so we need to catch it. We need to insert or attach a transmitter to it. We need an antenna and some kind of a receiver in order for us to pick up the signal that transmitter transmits. And this is a very powerful technique, of course. Right, so just quickly, the main differences between radio and acoustic. If you use radio tags, you can track the fish in pretty much any way you like. You can track it from a plane or a boat, stationary receivers, but you have to stay away from deep waters and salt water, right? Whereas the acoustic telemetry, well, you're more limited when it comes to tracking fish. You typically rely on stationary receivers, but you can track your fish in deep and saline waters. And then, Johan, slugs, pit telemetry. This is Johan in my backyard. He brought this invasive species. He pit tagged them and released them in my backyard. I still don't know why. But then he went out and tracked them with a portable antenna, like the one that Alfredo was also using. So it's cheap, it's very simple, but it has very limited range. Works fine for slugs though. Right, so the first example is from the River Po, where Florian and Alfredo and some others have been working on this fishway at the Casale hydroelectric plant. So it's a standard layout, if you like. You have the powerhouse, you have the fishway, and you have spillways. And here's the fishway up close. Right, so to study fish passage here, humongous pit antennas were installed in 2 locations, so the uppermost part and the lowermost part of the fishway. And then, of course, fish were pit tagged, and they were released at the lowermost part of the fishway and outside of the fishway to see at what extent they were using the fishway. So I won't go into details here, but here are some preliminary results. We can see that, and the species in red are invasive species. So there are more invasive species here than native. So we see that the barbel and the chub were pretty, I guess, 15%, is that high or low? Pretty good at finding the fishway and passing through it. And by the way, there were no major difference between the 2 release groups. Here are some other invasive species that didn't really perform that well, luckily, I would say. For example, the catfish. But then other studies and other parts of this data set show that, yeah, the big catfish can pass through the fishway, so it's not preventing any movements for them. Right, so we do know exactly what individuals that pass through the fishway and when, but similar to the mechanical tags, we don't have a clue what's going on with the remaining fish, the 85 to 90% fish that never turned up in the fishway. And obviously the next and the last technique is the use of acoustic telemetry. So a bit of overlap here also, James. This is the case that you presented yesterday. So the river Mörrumsån is a huge lake system in the uppermost part of the catchment. Then we have the main stem of the river with 5 hydropower plants in operation. There used to be a 6th one down here, but it was removed 3 years ago. And again, our task is to look at how this affects the salmon population. But the focus here is on these 2 plants. They have nature-like fishways for upstream passage, but the only downstream passage solution they have is the quick and dirty solution that I talked about earlier with let's open some spill gates. So this is what it looks like from above. So the direction of flow, the intake channel, spillways, and the nature-like fishway for upstream passage. Right, so looking downstream, intake channel, spillways, nature-like fishway. And this is where Sam, one of our PhD students, caught and tagged 120 salmon smolts and released them in various places upstream of the dams. So this is what James spent a year on. Luckily, before you came in to the project, James, we had, as you know, fish on land in various locations, which was a bit worrying. Anyway, so this is just one example of how one individual moved. It approached the spill gate and then decided, and went over here. And the idea now is that to combine it with the hydraulic models that we have to try to understand why fish do what they do, why they end up in the spill gate or not, basically, like many others in RIBES. Right. 60% of the smolts actually found the spill gate, which was higher than expected. But then the release here is 50%. So 50% of the water into the power plant and 50 is spilled on the side. And I'm not sure if I'm allowed to show this, James, but it seems like, so this is from the light experiment that Sam and James carried out. So James asked us to go there and turn the lights on and off, and we didn't really get it. But it seems like lights do have an impact on salmon smolt migration. So in darkness, so at night without any lights on, we had a very high passage performance. Whereas when the lights were turned on, it was quite similar to what we saw in daylight. So that's another thing we have to worry about then. It's not just a matter of the solutions, the mechanical solutions. We also have to worry about other factors. So why is telemetry the ideal tool for evaluating fish passage solutions? Well, it's because we need the details to understand what's going on, why solutions are working and not working. So this is the typical barrier with a fish passage solution, direction of flow. So we're looking at an upstream moving individual, tagged of course. We need to know if it's motivated. We need to know if it is interested in moving upstream. Next step is to find out if it's attracted to the fish passage solution, if it enters, if it passes all the way through, and if it continues upstream. This is the only way we can figure out what's wrong or what is not wrong, hopefully, with the solution in question. And again, the figure by Silva and Karopoulos showing the flow patterns and all these different phases of fish passage. But of course, most projects use multiple tools, use a combination of tools. And that brings me to the last short bit with the two multi-tool case studies. So again, the Hatting HEP that I claim is a functional two-way passage facility. And here we used pretty much all tools when we evaluated it over 10 years. So the old solution was a technical fishway, a Daniel fishway, very steep, fast-flowing. It was replaced by the enormous nature-like fishway with the fish counter up here. And for downstream passage, we went from a conventional trash rack with a trash gate over here to an angled rack with a bypass. All right, and we used pretty much any method that you can imagine to catch fish and track them and so on. And this is the summary of the results. We have we have improvements in passage efficiency for salmon spawners, sea lamprey, juvenile eels, even though we couldn't give you a specific number here. We can just say that the catches upstream increased after the modifications. And for downstream, perhaps even more spectacular, since we have pretty much 100% for salmon kelts, salmon smolts, and European silver eel. And the next step here is to develop a tool for fishway designers, since we will use our high-resolution eel data and try to figure out using machine learning to create this tool. And this is also a 3-year postdoc opportunity for anyone interested in machine learning and AI. Right, so I couldn't help myself, but I have a minute or two, I think. Yeah. Right, so we had the opening ceremony for this screw turbine last week, so I just had to include it. It's one of those unconventional solutions with quite an interesting potential. So obviously it's an Archimedes screw. It produces electricity, but it also has a second screw inside the big Archimedes screw. So at least in theory, it can pass fish upstream and downstream while producing electricity. Right, so we have fish counters in place, and we saw these guys pass through the nature-like fish way, not the screw, within the first week. I don't know if you had time to spot the catfish down here. So the Italians would go, ugh, and we go, yay, because it's native and it's threatened for us. So we like catfish. Right, so it will be more than video counters. We will use hydraulic modeling in collaboration with Politecnico, and we will use the high-resolution acoustic telemetry to map the movement trajectories of each fish and again, try to understand why they end up where they do and why they find or don't find the entrance to the screw turbine. Right, so this is the short and powerful take-home message that I promised. Pretty basic, but super important. We need evidence-based river restoration tools. Agree? Thanks, Chris. Right, so that was it. Questions?